Now let's look at the proof of the first claim, and I will only show first that the positive variation is monotonically non-decreasing, and I will leave the case for the negative variation to be monotonically non-decreasing as an exercise. So to show that this positive variation is monotonically non-decreasing, so let P be a partition of this interval Ax. So A is T0, then you have points T1, T2 up to Tn. This is equal to x, and let also x prime be a point greater than or equal to x. This is still less than or equal to b. So we will show that given any partition P of Ax, there exists a partition P prime of Ax prime such that we have that the sum j in I plus P of these terms ftj plus 1 minus ftj is less than or equal to the sum j prime belong to I plus of P prime ftj plus 1 minus ftj prime plus 1 minus ftj prime. And in fact, it's quite easy to create this partition. In fact, P prime can be taken to be, so start with, so it's just an extension of P to this interval Ax prime. So we have all the points that we already had up to x, and then we have Tn plus 1, this is equal to x prime. So this is just adding one more point in the partition, and you have immediately this inequality, because the sum on the right will contain the sum on the left. So this inequality star follows immediately. And therefore where plus f Ax is monotonically non-decreasing. So similarly, and I leave it as an exercise, that where minus f Ax is monotonically non-decreasing. Now to show that these two are in fact bounded, I will just again use the positive variation as an illustration of the proof is bounded. In fact, I'm going to show that where plus f Ax is less than or equal to the total variation or the variation of f over Ax, and this is less than or equal to the total variation Ab, and this is finite because f is of bounded variation. So we will show this. So it's not very difficult to show this. Again, this is about extending partitions. So let P be the partition of Ax. So A equals T0, T1, T2 and so on, and we have Tn equals x, and we have immediately that j in I plus P of this sum ftj plus 1 minus ftj is less than or equal to the whole sum j equal to 0 to n minus 1 f modulus of f tj plus 1 minus f tj, because again the sum on the right contains all the terms on the left. So this means that where plus f ax is less than or equal to where f ax, and it's immediate that this is less than or equal to the total variation over AB, which is finite. So it's also bounded, and so we have shown that the positive variation is both bounded and monotonically non-decreasing. And as an exercise, again you should show that where minus is also bounded. So this proves the first part of the claim. So let's go back to the claim. This proves the first part, which says that both these functions where plus and where minus are bounded and monotonically non-decreasing. And on the other hand, we have this formula fx minus fa should be equal to the difference of these two functions where plus and where minus. So let's try to show this. So proof of part 2. To show this, choose partitions. So first of all, let epsilon greater than 0 be given, and now we can choose partitions P1 and P2 of Ax such that we have the modulus of where plus f Ax minus this the sum f t j plus 1 minus f t j j in I plus of P1. This difference is less than or equal to epsilon, and similarly the negative variation we can take, let's take a different index, let's say k in I minus P2. The point here is that when you are using the supremum definition of the positive and negative variations, which is the supremum over all partitions, then for a chosen epsilon, the two partitions that you get when you get closer and closer to the supremum may differ when you take the positive variation and the negative variation. So here P1 might be different from the partition P2. So here we have for the negative variation minus of f tj plus 1 tk plus 1 tk plus 1 minus f of tk. This is also less than or equal to epsilon. And now we take a common partition, common refinement of the partitions P1 and P2. So let's call this common refinement say P, such that on this common refinement we still have that where plus minus f. So I am just putting both inequalities in one formula, j in I plus minus P. Now this is the sum of plus minus f tj plus 1 minus f Tj, this is less than or equal to epsilon. So this passing to the common refinement is a little bit tricky, because the set of indices, let's say for the positive variation, when you pass to the common refinement, then this index set I plus P1 might be different from I plus P, and similarly I minus P2 might be different from I minus P. So let's see a graphical representation of the changes in the index set I plus and I minus that can occur. Here I have denoted in the green points, in the green colored points, the partition P2 that we used for the negative variation, and in the red colored points the partition P1 that we used for the positive variation. And we suppose that T0 and T1 belong to I minus P2, I minus P2, which means that, so Ft1 is less than or equal to Ft0. So this is the situation here, Ft1 is less than or equal to Ft0, but when you plug in the partitioning from P1, which was for the positive variation, then it could happen that T0 is no longer in I minus, because at S0, so the partition now is T0, S0, T1 and so on, so according to the increasing order of the points. And here we have f of T0 is less than f of S0, and therefore T0 is no longer in I minus, but it's in I plus of the new partition P. But I still we will still have that this variation will still be close to the for the sums given by I plus P and I minus P. For both positive and negative variations, the sums will be at most epsilon away from the positive and negative variation. So I'll leave it as an exercise again. Exercise: check all possibilities to ensure that the inequality where plus minus f a x minus j in I plus minus p a modulus of, or rather plus minus f t j plus 1 minus f t j is less than or equal to epsilon. So even though we can have changes in the index set, we will still have this inequality. So once we have this, then it's not very difficult to show that fx minus fa is also close to the difference where plus and where minus by 2 epsilon. So let's see first that, note that small f fx minus fa is equal to the sum j over I plus p f t j plus 1 minus f t j minus k in I minus p minus f t k plus 1 minus f t k. So this is simply by using the sort of a telescoping sum, which is broken up into two pieces, one for the positive index set and one for the negative index set. So check this formula holds. And secondly, we have that f mod of fx minus fa minus var plus f ax minus var minus f ax. This is now less than or equal to the sum. So this is var plus f ax minus j in I plus p f tj plus 1 minus f tj plus var minus f ax minus k in I minus p minus I minus p minus f tk plus 1 minus f tk, and these two, both these terms are less than or equal to epsilon. So this is less than or equal to 2 epsilon, and since epsilon was arbitrary, we have equality of these two terms. So this shows that f is a difference of two bounded monotonically non-decreasing functions. So one is given by var plus fax plus fa, and the other one is given by var minus f. So this proves the statement of the lemma.